Hello everyone, my name is Shelby Lipham. I'm a senior majoring in chemistry medical science at Mississippi College, and I'm part of the computational chemistry group here at MC led by Dr. Majors. Today I will be discussing the relative energies of diastereomeric xanthene complexes for use in developing chiral sensors. So what is a chiral supramolecular sensor? Well, different enantiomers of chiral compounds can produce different pharmacological effects in biological systems. The enantiomer of a known therapeutic compound may have immensely different biological effects, including toxicity. Because of this, it is important to detect and control the chiral purity of pharmaceutical compounds. We have current chiral sensing methods involving chromatographic techniques, but they require expensive instrumentation. Chiral supramolecular sensors could reduce the cost significantly, and they're capable of intracellular monitoring, but they often lack the sensitivity required. Our research is focusing on finding a chiral supramolecular sensor that is sensitive and can give us a big energy difference between the R and S enantiomers when it binds to our complex. This is the xanthene complex that we chose to use in our study. You can see that it has a chlorine in the 3rd position shown in green, an amino group in the 6th position shown in blue, and a benzoic acid in the 9th position of the xanthene rings. In the benzoic acid ring, the acid group is ortho to the xanthene rings. This image shows R-phenylglycinol, which is the first analyte we chose to run calculations on. Here is S-methylbenzylamine, which is the second analyte that we ran our calculations with. So how does a molecule even detect chirality? We know that R and S enantiomers of a molecule should have the same energy because they're mirror images of each other. When they bind to a complex, the energy difference will change, and so we can tell which enantiomer is binding to the complex by finding the relative energies of each molecule. There should be a large difference in the energies to say that the sensor is sensitive enough to where we would be confident to say that it prefers one enantiomer over the other. The calculations ran for norepinephrine and phenylethanol were done in a previous study, so I won't discuss those results here. But as you can see in the table, we ran the calculations using 2 different functionals, the first being B3-lip and the second being MO6-2X. If you look at methylbenzylamine, you can see that the R conformation was the lowest in energy using the B3-lip, but the S conformation was the lowest in energy using MO6-2X, so these provided inconsistent results. If you look at the bottom of the table, you can see for R-phenylglycinol, the R conformation was the lowest for MO6-2X, and the S conformation was the lowest for B3-lip. Because we got such opposite results for these calculations, we decided to add another functional to see what would happen. We introduced the calculations using omega B97XD, and we got pretty consistent results between that functional and the MO6-2X. These results encouraged us not to trust the B3-lip calculations as much, not only because it was the only one that didn't necessarily agree between all 3 functionals, but because the B3-lip is a much older functional and it has no way to address dispersion interactions accurately, which is what we're running our calculations with, because these large molecules are using dispersion forces to interact, and the MO6-2X and the omega B97XD are both functionals that can calculate dispersion interactions. So we're going to be looking at these two functionals from here on out. You can see from this table that the S enantiomer is the lowest in energy for MO62X and omega B97XD for both double zeta basis sets and triple zeta basis sets. This is the energy table for the methylbenzylamine xanthine complex. After we ran our calculations in the gas phase, we decided to add solvents to our calculations because when we're making these molecules in the lab, realistically they're going to be in the solvent phase. And so what we found was that adding solvents to our calculations changed the energy significantly. It actually changed conformations of the molecule, and it also changed in one instance which conformation was favorable to the xanthine complex, which we found extremely interesting. So here we added acetonitrile to our calculations with the methylbenzylamine xanthine complex. You can see that the S conformation was the lowest in energy for the MO62X, but interestingly, the R conformation was lowest in energy for the omega B97XD, which contradicts our calculations we found in the gas phase. This is the same for both double zeta basis sets and triple zeta basis sets, because the R conformation for the triple zeta basis set is the lowest, and the S is the lowest for MO62X. For the addition of toluene as a solvent, the results pretty much stayed consistent in the gas phase and in the solvent phase because the S conformation was the lowest in energy for both MO62X and omega B97XD for double zeta and triple zeta. However, the conformation of the molecule did change, which we'll talk about in a moment. So this image shows the molecules on the left in the gas phase and then on the right with the solvent. You can see the xanthine complex at the bottom, and then methylbenzylamine is at the top interacting with the complex. So on the left, the conformation, we called it conformation 1, but this is how it favorably interacted with the complex. And then whenever we added acetonitrile to the mix, the conformation completely changed, so we called this conformation 2. The same occurred with the S enantiomer. So on the left here you can see the S enantiomer of methylbenzylamine interacting with the xanthine complex in the gas phase, and then when we added acetonitrile, the conformation changed, and you can tell a big difference here in the two pictures. So while some of our calculations provided inconsistencies, it was interesting that changing up certain aspects of the calculation, such as like adding solvents, changed the energy so differently. And so in the future we'll focus on changing solvents to see how that affects our calculations and our energies, and then also changing substituents on the xanthine rings, and maybe changing the analytes that we complex with the xanthine rings, all so that we can try and increase these energy differences, because our results, while they had a small energy change, they weren't large enough to be able to confidently say that they were sensitive enough to be used as chiral sensors. And so we would also want to try to introduce more functionals, since we saw that the B3 lip didn't agree with our other two functionals we used. We would want to introduce more functionals to see if we could get more data on that, since they did provide different results. And I would like to acknowledge and thank my research advisor and professor, Dr. David Majors, and also Dr. C.J. Stevenson from Loyola University in New Orleans. And thank you to the Mississippi College Computational Chemistry Group.